we have already seen information and how to implement application load balancers and network load balancers. Both load balancers have some things in common and some differences. Let's quickly compare the two, starting with the common features. The first common feature is the health checks. Health checks are used to determine if the target is healthy. Applications load balancers support health checks by HTTP, HTTPS, and gRPC. gRPC is an open-source remote procedure call, or RPC framework. It is commonly used by applications built on a microservices-based architecture. Network load balancers, on the other hand, support health checks by TCP, HTTP, and HTTPS. Both load balancers support logging via an AWS service called CloudTrail. Both load balancers also support load balancing to multiple ports on this same destination, and this is done by creating multiple listening agents. The next common feature is session stickiness. This allows routing requests from the same client to the same destination and is configured at the target group level. The next common feature is connection draining. When enabled, the load balancer stops sending requests to targets that are dropping or unhealthy while keeping existing connections open. This allows the load balancer to complete requests in progress, that is, requests that are already being serviced. When disabled, connections to the dropping or unhealthy targets are immediately closed and ongoing requests are not completed. Both load balancers also support cross-zone load balancing. When enabled, each load balancer node distributes traffic evenly among targets in all enabled availability zones. This means that it is not necessary to maintain the same number of instances in all availability zones. The next common feature is SSL offloading. This allows you to terminate, that is, offload the SSL connection to the load balancer, instead of terminating directly to the target server. The load balancer will decrypt the request from the clients before sending it to the registered targets. This reduces the CPU load on the targets, since SSL decryption is a CPU-intensive task. These are the common features. Now let's talk about the differences. The first difference concerns the OSI layer at which both load balancers operate. The ALB operates at layer 7, while the NLB operates at layer 4 of the OSI model. As I mentioned earlier, OSI stands for Open Systems Interconnection. The OSI model provides a conceptual framework for network communication and divides it into 7 layers. Each layer is responsible for certain tasks. Layer 7 is the application layer, and Layer 4 is the transport layer. The next difference is in the listening protocols. ALB support HTTP, HTTPS, and gRPC as listening protocols, while NLB supports TCP, UDP, and TLS. The next difference is in the supported targets. With the ALB, you can add an IP address, EC2 instances, or land a function as a target. With the NLB, you can add an IP address, EC2 instances, or ALB as a target. The next difference is support for elastic IP. This is only supported in the network load balancer. Adding an elastic IP address provides a fixed entry point for the network load balancer. The next difference is slow start. Slow start gives targets time to warm up before the load balancer sends them their full quota of requests. This is only supported on the application load balancer. Next is routing based on the source IP. It allows routing requests to a target group based on the source IP address of the requesting client. This can be useful in different situations, such as when you need to forward requests from a specific IP address to dedicated targets. This is only supported in the application load balancer. Next is path-based routing. It allows you to forward requests to targets based on the path or pattern of the requested URL. It is only supported in the application load balancer. Next is host-based routing. It is useful when serving traffic from multiple domains using the same load balancer. The incoming request can be routed based on the domain name specified in the host header. This is only supported in the application load balancer. And finally, we have support for custom HTTP responses. This can be used to respond with custom HTTP response codes, such as HTTP 200, 400, and 503. This has several use cases, a common one being error handling. You can customize the error response sent to the requesting client, thus improving the user experience. This is only supported in the application load balancer. As you can see, there are several commonalities and differences between the two load balancers. It is important to review these and your application requirements before selecting one to handle your traffic.